Welcome to my YouTube channel. Today I'm talking about standard error. So, standard error is different from the method of central tendency and the method of spread that we've been talking about. Because standard error, while it looks like it would be a method of spread, just like standard deviation, and I guess it is in a way, but not in the way you'd immediately think. So, standard error is actually the standard deviation of theoretical mean taken from a population. So if you take a sample, the average and standard deviation would not depend on n. It does not matter how many you take, 10 or 1,000, it would not systematically decrease or increase based on n. It is just what it is. But standard error, on the other hand, will decrease based on n. That's because your estimates are getting better with a larger n. And to demonstrate this point, I have R pulled up. I might have promised that I wouldn't use R, but I feel like this point really needs graphics to illustrate rather than me just talking about the difference between standard error and standard deviation. Okay, so in this code I have a theoretical population of 1 million individuals or whatever. The mean is set to 5 and the standard deviation is 1. So I run that code and it populates my environment and we get a histogram. Now the histogram is necessarily centered at 5 and the standard deviation is 1. So most of the points will fall between 3 and 7. Okay. So let's talk about sampling from this distribution. So I'm going to take one sample of size 20 from this population of 1 million. So I take the sample and I print the mean and standard deviation of that sample. Let's do that again, make it closer. Okay. Okay, I'm going to do a larger sample just so you can see that I am not crazy. Okay, so I'm doing a sample of 2,000 now. Okay, so the mean and standard deviation reflect the mean and standard deviation of the population. It does not matter how large I go, it will always be a mean of around 5 and a standard deviation of around 1. Because that's the population mean and standard deviation. It would not systematically go to 0 or do anything crazy. If I do 200,000 here, it's going to be 5 and 1. It just wouldn't reflect my point when it was 20 because there was too much variability in that. And that's actually what we're going to be talking about. We're going to be talking about the variability in sample means. So when we had a smaller sample, the variability in parameter estimate was greater. It's not 4.99, it's 5.48. And that's actually what we're talking about. We're talking about the variability in sample means. So if you were to repeat the sampling many times, what would the standard deviation of the distribution of that be? And I know that it is more abstract than thinking about the mean and standard deviation of a single sample. So I've done a small simulation where I repeat this process 1,000 times for a sample size of 20. And I'm going to go ahead and run that. Okay, so now we have 1,000 sample means. So each time we sampled from the population 20 individuals, and we took the mean of that. And we did that over 1,000 times, and we got this distribution. Okay, so let's take a look at the differences between the other one and this one. So, the bars look different, but that's bandwidth. That's not like a property of the distribution. It does look different because of how our default system divided the bars. So we're not looking at that. We're looking at the spread of the distribution. So this still has a mean of 5. It will always have a mean of 5. That does not change. But what does change is the spread of the mean. Okay, spread from the mean, not of the mean. The spread of the mean, it becomes more confusing, and that's why I decided to use R to demonstrate this. Okay, so it looks like the standard deviation is probably around 0.5. Because it goes from 5 to 6. And all the data is probably about 2 standard deviations out. That's not true. That's only 95%. There's another 5% past that. But I'd say the standard deviation is about 0.5 compared to a standard deviation of 1. So 5. This has to go out further than you think. So 7. It goes out further, but it's also a sample of 1 million. So you see a lot of, you see the tail filled out. But that's about 95%. From 5 to 7 and 5 to 3. So anyway, the estimates become more narrow, and that's not a property of the individual sample distributions. That's a property of the estimated means. As you collect more, like, as the sample size of the sample becomes larger, your estimates become more narrow. So, I should probably really pin down what I'm talking about here. And actually, I was wrong. It's 0.228, or no. Yeah, that absurd standard deviation was 0.228, and the theoretical standard error would be 0.223. It's about the same. Okay, so what dictates the standard deviation of the histogram? And apparently, my approximations aren't that great. But anyway, what dictates it is the sample size of each individual sample. That sample size of 20 makes it more narrow. It's not how many means I collected. I collected 1,000, but I'm not going to get significantly different results if I do 100,000. It'll take longer to run, but it won't be significantly different. Give it 1 second. And I guess I could have illustrated my point with 10,000. Okay, so like I was saying, the standard error calculation is standard deviation, the sample standard deviation. You do not have the population standard deviation, because if you did, you just use that. Divided by the square root of n. N is the sample size of your sample. So, in my example, it's 20, and I get a certain standard error based on that. In your example, it may be larger or smaller. The larger the sample size, the more it's going to decrease the standard error. And I'm regretting not using 10,000. Let's keep looking here. So how do you calculate standard error? Well, first, you do all the steps to calculate standard deviation. And that's in my previous video. The video before this is standard deviation. The video before that is variance. And the video before that are mode, median, and mean. I know that because I'm doing these all one after another. That's why I started adding things. Okay, so you calculate the standard deviation, and then you divide by the square root of n. Okay, and my calculation finished running, so we'll talk about that in a second. Okay, so the number of means did not affect the outcome, although the standard deviation of those means did get closer to the theoretical 0.223. My point being that what determines the standard error isn't the number of means, because in real life, you're only calculating one mean. You're taking one sample and calculating a mean from that. Well, what we're saying is, if you did replicate that 1,000, 100,000 times, the standard deviations of those means is predictable. You know what they will be based on statistical theory. And we can do this by simulation. If I did sample sizes of, say, 50, I know what they ought to be. So we would take that population standard deviation divided by the square root of 50, and we'll get a predictable result. Whatever 1 divided by the square root of 50 is. And I don't know what it is. And I don't need to know what it is. It's 0.141, apparently. And the histogram became even more narrow. So why is this useful? So when we take a sample mean, the standard error tells us about how close we are. We take the mean and we add we do plus and minus 1.96 times standard error, and we get a confidence interval for where we believe the mean would be in the population. If you did this sampling 1,000, 10,000 times, how good of an estimate is your mean based on that sample size and the standard deviation of the data? Okay, so I'm going to try to wrap up because I want to. Okay, so standard error. So it gives us an idea of the variability we'd expect from estimating a population mean, not in the sample. Standard deviation is talking about the spread of the data in the sample. Standard error is the theoretical variability in your mean estimate for your sample. And you're not going to do more than one sample most likely, but it follows this general course that the standard deviation of your sample mean, that we call standard error, will be your sample standard deviation divided by the square root of n, or your sample size. So it's easy to confuse these two topics, and that's why I'm spending some time on it and trying to repeat myself. So standard deviation, talking about the sample. Standard error is a proxy measure for how variable your sample means would be if you repeated the sampling process many times independently. Okay, so that's the end of the video. Thanks for watching.